Right. Please write the heading. Oscillations and waves. Oscillations and waves. Star point and write. There are three major sections in this lesson. Please don't doubt. Please write. I know what I am doing, so no mistakes are done. Please write. Heading, oscillations and waves. Star point. There are three major sections in this lesson. Number 1, 2, 3. Number 1, simple harmonic motion, which is said to be SHM, simple harmonic motion. Second one, second section, mechanical waves. This is what we are going to start today. We are going to start mechanical waves today. Third section, ray optics. Mostly known as the light lesson. Right? So this lesson has three major sections. Please write them. Okay? So write the main heading as mechanical waves. Heading, subheading is waves. So today I'm starting the second section of this lesson, mechanical waves. You have learned a lot of things about waves even in O-level science, right? So you can easily continue this lesson. You can easily learn this lesson because you are here after passing O-level science. You have learned them. So heading, Lamai, heading is mechanical waves. Subheading is waves. Online people, they didn't see the subheading waves. What is a wave? What is a wave? You. Online people send a message to Zoom chat saying what a wave is. A distance measured disturbances which are propagating. U. Very good. 90% of the answer is correct. U. 90% is okay. U. What is a wave? U, dear. This one. මම ප්‍රශ්නේ අහයි කියලා වතුර බොනවා. You. Disturbances. ඒ කියන්නේ wave කියද්දි ඔයාලට මතක් වෙන්නේ disturb කරනවා කියලාද? You dear, what is a wave? It's an oscillation. Yes, good, nice. You dear. Try. This is a new lesson. Everybody should be able to learn. Everybody should be able to study, understand. What's a wave? As you think. You dear. It's an oscillation. Try dear. Give me the way you feel when you hear the name waves. Disturbances. Movement of particles. Wow, good. You dear. ඔයාට මොනවද හිතෙන්නේ wave කියද්දි? You dear. ඉස්සරහට ඉන්න බෑ. ඇයි ඔතන ඉන්නේ? Come to the front. Is it comfortable there? What's the wave? You. Transferring of particle from one place to another place. You dear. Vibrations of particles. Hondai. You. Oscillation. Oscillations. The most common answer, oscillations and disturbances. බලමු online ළමයි මොකද කියන්නේ කියලා. Disturbances that travels through physical medium. ඒ කියන්නේ ඔයාලට ඉරේලියම් පේන්නේ නැද්ද? Sunlight, can you see sunlight? Good, nice. What is the sun there? Sun is the nearest star to the earth. Sun is a star and it is very closer to us when compared to the other stars. What we are receiving from the sun? We receive light. Light brings us energy. That's why we convert light energy into electrical energy by using solar panels. Okay, dear? So it means light rays travel from sun to the earth. Right? Right. Light rays. Wow. Let's say this is the sun. This is the sun. It's a star. This is us, the earth. What does the sun do? It sends us electromagnetic waves. Light is a kind of electromagnetic wave. Sun sends us electromagnetic waves. One of the well-known electromagnetic wave is light. So sun sends us electromagnetic waves. Right? One of the main electromagnetic waves sent by the sun is the light, and we are able to see the light. As light brings energy from sun to the earth, we can convert light energy into electrical energy. There must be energy in the light waves, otherwise we can't generate electrical energy from them. We use solar panels. Got it, dear? So it means these electromagnetic waves, they have transferred energy. So what's the main job done by a wave, dear? They transfer energy. And they are not doing one major thing. That's why we are here. Otherwise, all the living beings on the earth will die, will be burnt, killed, and destroyed if the waves transfer materials or particles. Why? Temperature of the sun is about 6,000 degrees Celsius. Therefore, all the particles on the sun has a temperature, they have a temperature of 6,000 degrees Celsius, 6,000 Kelvin, right? Slightly greater than this. If particles at 6,000 Kelvin travel with the waves and incident on the earth, we will definitely be burnt. Then it is so much confirmed that particles are not traveling with the waves. Waves do not transfer materials, but waves transfer energy. Therefore, waves are the things which transfer energy without transferring the materials. When a wave travels in a material medium, particles will be oscillated. When electromagnetic waves travel, they disturb the electric fields and magnetic fields. So those disturbances and oscillations are there when a wave travels, right? But we can't say wave is something traveling because I am traveling. Am I a wave? I am oscillating my hand. Is my hand a wave? I transfer some energy with me, kinetic energy. Am I a wave? No. A wave will transfer energy, but it should not have transferred materials. Got it? So you have written the subheading as waves. Under the subheading of waves, please write a wave is a thing. Leander Babu. A wave is a thing which transfer energy. A wave is a thing which transfer energy, comma, without transferring the materials. A wave is a thing which transfer energy, comma, without transferring the materials. Okay, dear? Next star point. For an example, let us consider the electromagnetic waves. For an example, let us consider the electromagnetic waves travel from sun to the earth. For an example, let us consider the electromagnetic waves travel from sun to the earth. Right? Lamai, please draw this figure. Draw this figure. below the figure, star point and right, the electromagnetic waves transfer energy from sun to the earth. From sun to the earth. The electromagnetic waves transfer energy from sun to the earth. Full stop. But they do not transfer particles, within brackets materials. But they do not transfer particles, within brackets materials, from sun to the earth. From sun to the earth. Okay, dear? Next star point. The temperature of the surface of the sun is, about 6,000 degrees Celsius. Maybe 6,273. I would like to use a rounded off value. The temperature on the surface of the sun is 6,000 degrees Celsius. Full stop. If the particles travel with the electromagnetic waves, comma, if the particles travel with the electromagnetic waves, comma, the particles which are at 6,000 degrees Celsius, the particles which are at 6,000 degrees Celsius, comma, will definitely burn the earth. Then there will be no earth, no life, nothing. The particles at 6,000 degrees Celsius will definitely burn the earth. Got it? Right? Do we experience such a temperature here? So we have never experienced such a thing. Therefore, it is confirmed that the waves do not transfer particles. Got it, dear? I'm not going to give you that much of details, right? Okay, so what is a wave? It is a thing which is able to transfer energy without transferring the materials. They transfer only the energy. For example, when I am talking, right, my sound waves generated by mouth travels to your ears. So sound waves brings energy. Those energy vibrates your eardrum, then you will hear my voice. What will happen when people are talking? If the particles are also traveling with the sound wave, what will happen? Then the population will be reduced. Why? There will be no love affairs, no marriages. Why? The particles of your mouth are good smelling. So when you talk, if those good smelling particles travel to your so and so, he will recognize the good smell behind the beauty. Okay, dear. So luckily, particles not traveling from mouth to the people who you are talking to with the mechanical waves, sound waves. Got it, dear? That's why he's still with you. Right. No, not the. Let's say your class teacher confirm that not transfer particles. Got it, dear? Right. Next star point. There are two different kinds of waves. Next star point. There are two different kinds of waves. Number one, Look at board and write mechanical waves. Mechanical waves. Number 2, electromagnetic waves. Electromagnetic waves. Electromagnetic waves. Right. There are two different kinds of waves, mechanical waves and electromagnetic waves. Next subheading, mechanical waves. Mechanical waves. Under that, please write are the waves that needs a medium to travel. Mechanical waves are the waves, comma, that need a medium to travel. That need a medium to travel. Leave a line and write examples. Leave a line and write examples. Number 1, sound waves. Examples. Number 1, sound waves. Number 2, waves on stretched strings. We will learn both. In this lesson, we will learn both. Number 1, sound waves. Number 2, waves on stretched strings. Okay? Then write the next subheading, electromagnetic waves. What is the next subheading there? Electromagnetic waves. Electromagnetic waves. Electromagnets, which a vibrating magnetic field, the waves which are generated by a vibrating magnetic field and a perpendicular electric field. The waves which are generated by a vibrating magnetic field and a perpendicular electric field, comma, are known as electromagnetic waves. Are known as electromagnetic waves. Electromagnetic waves. You read that star point there? Read it. I think now you can as electric field and don't want a medium travel. Yes, correct me. The light are in between sun and the earth. Online people, can you see the board clearly or not? Online people, please send a message to the Zoom chat saying whether you are able to see the board clearly or not. Right. Is the video clear or not? Online Lamai, is the video clear or not? Send a message to Zoom chat quick, dear. Right, good. So, if the electromagnetic waves need a medium to travel, we will be in fully dark. Why? The light rays will not travel from sun to the earth. So then it is confirmed that no medium is needed to travel for the electromagnetic waves. So please write examples. Examples. The best example for electromagnetic waves is light. The next example, you may have used them when you go to hospitals, X-rays. Third example, you learn in matter and radiation lesson, gamma rays. Under particle physics, you will learn gamma rays. X-rays, light rays, gamma rays, mobile phone waves, radio waves, TV waves, all of them are electromagnetic waves. Got it, dear? So, what are the things that we have learned so far? What are things that we have learned so far? Waves are the things which are able to transfer energy without transferring the materials. They just transfer energy. They do not transfer particles, materials. There are two different kinds of waves. They are known as mechanical waves and electromagnetic waves. Mechanical waves are the waves that need a medium to travel. Electromagnetic waves are the waves that do not need a medium to travel. Electromagnetic waves are generated by oscillating magnetic fields and oscillating electric fields. Right? You will learn about electric fields and magnetic fields at the end of the syllabus under electric fields and magnetic fields. Right? One of the well-known mechanical wave is a sound wave. That's what we are using to communicate. And one of the well-known electromagnetic wave is the light wave. In the third lesson, oscillation and waves, we learn everything about light waves and sound waves. Got it? Then let's try to identify the basics of waves. Basics, fundamentals, right? So write your next heading, ripple tank. Ripple tank. Ripple tank. Under that, please write a ripple tank is a transparent glass tank. A ripple tank is a transparent glass tank which is normally filled with water. A ripple tank is a transparent glass tank, which is normally filled with water, right? Same line, same point. It can be used to study basics of waves. It can be used to study basics, fundamentals of waves. Basics of waves. Same line, same point. An electronic vibrator is used to generate the waves. An electronic vibrator is used to generate the waves. Lami, what's the meaning of a transparent tank? You read the definition one more time. What's the meaning of transparent? It means light can travel. It means normally this tank is made of glass. Okay, dear? It's a glass tank which is filled with water, in simple terms, right? So, it's a glass tank filled with water, right? Right. Then we want to generate waves. To generate waves, we are using a electronic vibrator. Electronic vibrator means there's a rod, it can be moved up and down. In this electronic vibrator, there's a rod. This rod can be moved up and down. There's a metal ball also normally at this one. So this is moving up and down. Once this metal ball hits the water surface is bent and a wave is created. Got it? Draw the figure. Draw this figure. This is an electronic vibrator. Draw the figure quick. Right? Shall we continue? Who wants more time to draw the figure? Right. Star point and write. When the electronic vibrator is switched on, when the electronic vibrator is switched on, when the electronic vibrator is switched on, switched on, comma, the vibrating rod, that's what I have drawn here. The vibrating rod start to oscillate up and down, or start to oscillate vertically. The vibrating rod start to oscillate vertically or up and down. Full stop. Once the vibrating rod hits the water surface, once the vibrating rod hits the water surface, comma, a water surface wave is, once the vibrating rod hits the water surface, comma, a water surface wave is generated. A water surface wave is generated. Got it, dear? So when this rod is moving up and down, it hits the water surface and a water surface wave is generated, right? So you'll be able to see a wave like this. That's what you are able to see, right? Let me draw this figure. Right. So then you will see something like this, right? Draw this figure, and this is said to be a water surface wave. Lamai, wait, one more thing. Could you please name this point as P, and let me name this point as Q. PQ is the water surface, level of water at the beginning. And here also mark the PQ level using a dotted line. On this figure also draw a dotted line and mark P and Q points. P and Q points. Very important to mark these points. Right. Draw this figure. Star point and right. The wave travels from, we have marked P and Q letters. Star point and right. The wave travels from P to Q. The wave travels from P to Q. Am I right, dear? Next star point. A small piece of wood, a small piece of wood is placed on the water surface wave. A small piece of wood is placed on the water surface wave, comma, to check whether water is also moving with the wave from P to Q. A small piece of wood is placed on the water surface wave, comma, to check whether water is also move with the wave from P to Q. Whether water is also move with the wave from P to Q. Got it, dear? Right. Look at both. Look at both. We just placed a piece of wood. No need to draw a new figure. On the same previous figure, this is a piece of wood. We place a small piece of wood. We can't place a piece of metal. Why? Metals will sink. Metal will not float. If water travels with the wave, what should happen here? We have placed the piece of wood on water. If water flows, if water moves with the wave, definitely this wood piece should also move from P to Q. Can you understand? Wave travels from P to Q. We want to know whether water particles also move with the wave, travel with the wave into the direction of the wave. Then it can be identified that piece of wood is not moving horizontally, but it is oscillating vertically. This moved downward. After that comes rest and it moves upward. So you can observe that it is just moving upward and downward. Please mark this oscillating direction there. Use some arrowheads and show that the piece of wood is just oscillating upward and downward. It's not moving with the wave. Indicate it properly, dear. Right. Next star point. It can be observed that, next star point, it can be observed that the piece of wood is, it can be observed that the piece of wood is just oscillating vertically. It can be observed that the piece of wood is just oscillating vertically. Observed that the piece of wood is oscillating vertically, comma, while the wave travels horizontally. While the wave travels horizontally. While the wave travels horizontally. Full stop. Then it is confirmed that then it is particles. Then it is confirmed that the water particles do not travel with the wave from P to Q. Then it is confirmed that the water particles do not travel with the wave from P to Q. Got it? Read the star points once again, check whether you can understand. I think you are able to see the figure clearly. Okay? Right. So it's confirmed that wave travels P to Q horizontally. Water particles oscillating vertically. When the wave travels horizontally, particles of the medium oscillate vertically. Therefore, traveling direction of the water surface wave and the oscillating directions of the particles in the medium are perpendicular to each other. Such a wave we say to be O-level science. When wave travels to one direction, if the particles are oscillating perpendicular to the traveling direction, such a wave we say to be transverse waves. Very good. Transverse waves. Next point. The water surface wave travels horizontally. Next point. The water surface wave travels horizontally, comma, while the particles in the medium, here the medium is water, while the particles in the medium, oscillating vertically, while the particles in the medium oscillating vertically, while the particles in the medium oscillating vertically. Full stop. Therefore, the traveling direction of the water surface wave, therefore, the traveling direction of the water surface wave, is perpendicular to the oscillating direction is perpendicular to the oscillating direction of the particles in the medium. Oscillating direction of the particles of the medium. Therefore, the water surface wave is said to be a Lama use a different color pen and write. Therefore, the water surface wave is a, use a different color pen and write, transverse wave. Therefore, the water surface wave is a transverse wave. Okay, dear? So, what is the first special feature that we have identified by using the ripple tank, dear? Transverse wave. Wave travel to one direction, particle oscillating perpendicular to the traveling direction, right? That's the first thing we have learned. Write the next subheading, amplitude. Within brackets, capital A. Amplitude. What is amplitude, dear? Look at board. This is the PQ level. This is the water surface wave. PQ level is said to be the mean level. Mean level is the level where the water surface was at rest before the wave is started. Water surface was at rest at the PQ level before the wave is started. Therefore, PQ level is said to be the mean level. The other meaning of the mean level is if you measure this length, height, and if you measure this depth, they are equal. Right? So, that's the other reason to say the mean level. The maximum displacement of water particles from the mean level is said to be the amplitude. The displacement, the maximum displacement of the water particle from the mean level is amplitude. This is also a water particle. Its displacement from the mean level is the amplitude. So therefore, this is also an amplitude. Draw this figure. Below the figure, please write the maximum displacement from the mean level within brackets PQ level. The maximum displacement from the mean level within brackets PQ level is defined as the amplitude. The maximum displacement from the mean level within brackets PQ level is defined as the amplitude. Okay, dear? Right. Then let's go to the next important theory part. Right, look at board, dear. Write the next subheading as board same phase oscillations. Same phase oscillations. Same phase oscillations. Right. Lamai, let me use the same figure. I'll erase the amplitudes now because now I'm not interested in amplitudes. Let me draw the same figure. Let me use the same figure to explain same phase oscillations. Look at board. So this is the wave travels from P to Q. This time I'll take more parts. Look at board. Let me consider the point Q. Right. So what's really happening here? This water particle is just moving up and down. All the water particles in the wave is just oscillating up and down. If I consider this particle, which is here, let me say X, within next second, it will be moving downward because it has traveled to the topmost position. It cannot go further within next second, it will start to move downward. Similarly, if I consider this particle, which is at y, it will also start to move downward. If I consider the particle here, z, it will also start to move downward. Therefore, if you are looking at this wave, you will observe that all the xyz particles will be moving downward within the next second. And all the x, y, z particles will reach to the same PQ level at the same time. Got it? And if you wait further, these particles will reach to the bottommost positions at the same time. After that, they will start to move up. Got it? So it means motion of the particle x, y, and z identical. They always move together into the same direction. Their vertical heights will be the same always. They will be at the same vertical height always. Got it, dear? And they always move into the same direction. Therefore, we say x, y, z particles are oscillated in the same place. Okay, dear? Same phase. But if you consider this particle, this one, let me use the word letter capital A. When x is moving downward, A is moving upward. When A reached topmost position, x will be at the bottommost position. X will be at the bottommost position when A is at topmost position. When x start to move up, particle A will start to move downward. Therefore, oscillating directions of x and A particles are always opposite. Oscillating direction, moving directions of x and A particles are always opposite. Therefore, we say x and A particles oscillate in the opposite phase. Or, what's the best term there? Always opposite. What's the best term? Antiphase. Anti mean opposite. Always opposite. That's why you call your mother-in-law in one day anti-anti. Yes, yes, yes. Before the marriage, you ask her daughter. They say, no, I can't give you. After a few years of marriage, you want to go for another one. Then say, don't leave, stay with my daughter. Always opposes the things that you are going to do. That's why I call anti. After a few years, you can experience it, right? So x and A oscillate in the opposite direction. Always they are moving directions opposite. What about B particle? What do you think about particle B? When x is moving downward, B is moving upward. Again, x and B are particles in antiphase. What about A and B? They always move into the same direction. So, oscillating directions, oscillating pattern, the way of oscillation of A and B is same. Therefore, we say A and B oscillate in the same phase. AB oscillate in the same phase. YB antiphase. XA antiphase. Can you understand? Draw this figure. Write the heading same phase oscillations and draw this figure. Quick. More time to draw the figure? Okay, I'll give you 1 more minute. Right? When two or more particles always have the when two or more particles always have the same oscillating direction or same moving direction. I think moving is better. When two or more particles always have the same moving direction, comma, they are said to be oscillated in the same phase. When two or more particles always move into the same direction, comma, they are said to be oscillated. They are said to be oscillating in the same phase. They are said to be oscillating in the same phase. Okay, dear? Next star point. X, Y and Z particles. X, Y and Z particles are oscillating in the same phase. X, Y, Z particles are oscillating in the same phase. Next star point. Similarly, A and B particles are also oscillate in the same phase. Similarly, A and B particles are also oscillate in the same phase. Got it? Next star point. When X and capital A particles are considered, when X and A particles are considered, comma, their velocities are always into the opposite directions. When X and A particles are considered, comma, their velocities are always into the opposite directions. First stop, same line, same point. Therefore, X and A particles are said to be oscillated in the use a different color pen and write antiphase. Said to be oscillated in the antiphase. Use a different color pen and write antiphase. Said to be oscillated in the antiphase. Got it, dear? Next star point. Similarly, Y and B particles. Are also oscillated in the antiphase. Similarly, Y and B particles also oscillate in the antiphase. Got it, dear? So if you want, you can write B and Z also antiphase, but no need. Right. Now read the entire note under the subheading same phase oscillation. Read everything that are given under the same phase oscillation. Everything. Hmm? In O levels, how do you define wavelength? What is wavelength? The distance between the distance between any two consecutive threads or troughs. Threads mean මතකද? ඒ Y level වලට හරියන්නේ. In advanced level definition is wavelength is the distance between any two particles oscillating in the same phase. It means gap between X and Y is the wavelength. Don't mark them. Gap between A and B is also wavelength. Similarly, gap between Y and Z is also wavelength. Wavelength is normally represented by the letter lambda. So write the next subheading, wavelength, within brackets lambda, lamai, then draw this figure. It's very important. Write your next subheading saying wavelength, write lambda within brackets, draw this figure. Similar figure, but please draw it. Please don't be lazy. Draw this figure. Right. Who wants more time to draw the figure? Right. So if you go from x to y, you cannot find any other particle which is oscillated in the same phase with x and y. You cannot find any particle in between x and y in this section which is oscillating in the same phase with x and y. How to say it, dear? How to say in a single word that you cannot find any particle in between x and y oscillating with the same phase with x and y. How to say it in a single word? We say, have you ever heard, dear? Consecutive, right? So if I say x and y particles consecutive, it means you cannot find any particle which is oscillating with the same phase in between x and y. Okay, dear? Star point and write. It cannot be found, star point and write. It cannot be found any particle. It cannot be found any particle which is oscillating with the same phase in between x and y. It cannot be found any particle oscillating with the same phase in between x and y. It cannot be found any particle which is vibrating with the same phase between x and y, comma, in addition to the x and y particles. In addition to the x and y particles. In addition to the x and y particles. Full stop. Therefore, x and y are said to be, use a different color pen and write, two consecutive particles. Now use the normal color pen. Two consecutive particles. After that, use a normal color pen and write, two consecutive particles oscillating in the same phase. Therefore, x and y are said to be two consecutive particles oscillating in the same phase. Oscillating in the same phase. Got it, dear? Next star point. The distance between any two consecutive particles. The distance between any two consecutive particles. The distance between any two consecutive particles oscillating in the same phase. Two consecutive particles oscillating in the same phase. The distance between any two consecutive particles oscillating in the same phase, comma, is defined as the, use a different color pen and write, wavelength. Is defined as the wavelength within brackets lambda. Right, Lamai, now read everything that are given under the subheading of wavelength. Read all the things given under wavelength subheading. Right. I think you understood. Then, if you check, uh, let me mark this point as R. Lamai, would you please mark this point as R? I forgot to say it. Mark this point as R. Right. Star point and write. Capital P and capital R. Capital P and capital R are also two consecutive particles. Capital P and capital R are also two consecutive particles, comma, which are oscillating in the same phase. Capital P and capital Q are also two consecutive particles which are oscillating in the same phase. Therefore, capital P and capital R are also two consecutive particles oscillating in the same phase. Therefore, distance between P and R, therefore the distance between P and R, is also equal to the wavelength. Therefore, the distance between P and R is also equal to the wavelength within brackets lambda. Right? So, draw two dotted lines. Please draw two dotted lines like this and mark this gap is also lambda. Okay, dear? So, what is the advanced level definition of wavelength? It is the distance between any two consecutive particles oscillating in the same phase. One cycle. Bicycle නෙමෙයි. One cycle. Right. Lamai. Look at board. I use the same PQ wave. Where did we find this PQ wave? From the ripple tank water surface wave. මතකද දන්නේ ඒක? From the ripple tank water surface wave. Look at board dear. So what is wavelength, Lamai? Lamai, what is wavelength dear? It is the distance between any two consecutive particles oscillated in the same phase. Then, in the previous session, I have said that P and R particles also oscillated in the same phase. Therefore, P and R, gap between P and R is also equal to the wavelength. Right? So, one cycle means when a wave travels a distance equal to the wavelength, it is said that wave has completed one cycle. In O levels, when I ask what is one cycle, they say, so meme. So meme එකක් wavelength එකයිලු. meme නෙමෙයි. එහෙම අත හොල්ලන්න බෑනේ විභාගෙට ගිහිල්ලා. So what do you say? When a wave travels a distance equal to the wavelength, it has completed one cycle. So draw this figure one more time and name this as one cycle. One cycle. Draw this figure one more time. Clearly name one cycle. හරිද? We are using a ripple tank to understand, to identify basic features of waves. What are the basic features, dear? Amplitude, same phase oscillation, antiphase oscillation, wavelength, one cycle, time period, frequency, velocity. So they are said to be the basic features. Now we have completed up to wavelength. Let's write. Who wants more time to draw this figure? Right, below this figure, please write. When a wave travels, when a wave travels a distance equal to its wavelength. When a wave travels a distance equal to its wavelength. When a wave travels a distance equal to its wavelength, it is said that the wave has completed one cycle. When a wave travels a distance equal to its wavelength, it is said that the wave has completed one cycle. It is said that the wave has completed one cycle. Got it? Next subheading, the time period. The time period within brackets capital T. The time period. No need to draw any figure. Just write the time taken for a wave. The time taken for a wave the time taken for a wave to complete one cycle. The time taken for a wave to complete one cycle is defined as the time period. The time taken for a wave to complete one cycle is defined as the time period. Got it? Now I look at board here. For example, let's say this wave takes 2 seconds to travel from P to R. Then we say time period is 2 seconds. When the wave travels a distance equal to the wavelength, it completes one cycle. Therefore, when the wave travels from P to Q, it has completed one cycle. To complete one cycle, it has taken 2 seconds. Therefore, we say time period is 2 seconds. So, what should be the SI unit of time period then? Seconds. Seconds. Got it? Star pointer right. The SI unit of star point. The SI unit of time period is seconds. Seconds. The SI unit of time period is seconds. Right? Next subheading, frequency. Within brackets, simple F. No need to draw any figures, right? Don't worry. Don't blame me. Frequency. Within brackets, simple F. Please write number of cycles. Number of cycles completed per unit time. Number of cycles completed per unit time is defined as frequency. Number of cycles completed per unit time is defined as frequency. Star point and write. If a wave completes 10 cycles for 1 second, if a wave completes 10 cycles for 1 second, comma, its frequency is said to be 10 hertz. What is the SI unit of frequency, dear? Hertz. We have learned all these things under units and dimensions lesson, right? Hertz. Right? If a wave completes 10 cycles for 1 second, its frequency is 10 hertz or 10 cycles per second. Okay, dear? Right. Star point and write. Let us consider a wave. Star point and write. Let us consider a wave with a frequency of, look at board. Let us consider a wave with a frequency of simple F hertz and with the frequency of simple F hertz and with a time period of capital T seconds. Capital T seconds. Let us consider a wave with a frequency of simple F hertz and with a time period of capital T seconds. Got it, dear? Right. First statement, lian lamai. The frequency of the wave. The frequency of the wave equals simple f hertz. The frequency of the wave, equation mark, hertz, f hertz. Next statement, you will need 2 lines to write the next statement. You may need 2 lines to write the next statement. Therefore, number of cycles completed for 1 second. Therefore, the number of cycles completed for 1 second. Number of cycles completed for 1 second equals, how many cycles will be completed, dear? Number of cycles completed for 1 second is f. That's why we say frequency is f. If we say frequency is f, the number of cycles completed for 1 second is f. Then I write the inverse of the second statement. Inverse of the second statement means, look at board, therefore, the time taken, therefore the time taken to complete simple f number of cycles. Therefore, the time taken to complete simple f number of cycles. How much? How many seconds? Within 1 second, f cycles are completed. Therefore, time needed, time taken to complete f cycles is 1 second. Write it. Just 1 second. Write the 3 statements. Read the 3 statements. Frequency simple f. It means number of cycles completed for 1 second f. F cycles are completed within 1 second. Therefore, time taken to complete f number of cycles is 1 second. Next statement, please write with me. Therefore, the time taken to complete one cycle. Therefore, the time taken to complete one cycle. How do we find this? Time, let's say time taken to complete f number of cycles, let's say t seconds, for example. What's the time taken to complete f number of cycles, dear? T seconds. Therefore, time taken to complete one cycle, how do we find? T over f. Am I right? Time taken to complete f is t. Therefore, time taken to complete 1 t over f. Can you understand? Now, instead of t, we have 1. Therefore, this should be 1 divided by f. Can you understand? Would like if I explain this again? The method is using t. Instead of here, you use any number. When you write, when we write 1 second, some students are confused. So it means time taken to complete one cycle is less than 1 second. Got it? That's right. Time taken to complete f cycles, 1 second. Therefore, time taken to complete one cycle, 1 second divided by f. Star point and write. Star point and write. But the time taken to complete one cycle is, but the time taken to complete one cycle is defined as the time period within brackets capital T. But the time taken to complete one cycle is defined as the time period. Got it? Within brackets capital T. So it means what is this, dear? What is this? So this is the time taken to complete one cycle is 1 over f. Therefore, look at both. Therefore, the time period. Therefore, the time period equals 1 over f. Write it. Now read all the statements from the very beginning. Check whether you can understand. It's better if you can understand. Read. So, look at board. We want to write one more step. So I'll write it here. Final thing is therefore time period capital T equals 1 OF. Leave a line and write this relationship also. Okay. So I have proved that time period is equal to 1 over F. Okay. Right. Lamai may balant. May balant. If I rewrite the relationship that we have already obtained. What is the relationship that we have already obtained here? T equals 1 over F. It means time period equals 1 over frequency. Now, if I interchange F and T, I take F to the place of T and T to the place of F, I will get this relationship. I will get F equals 1 over capital T. So saying a note, please write this. This is what we are going to use next. This is the relationship that we are going to use next. Please draw an arrow and name this as, this is a very important relationship, name this as frequency. Frequency. So frequency is equal to 1 over capital T. T means time period. Would you please name there? So frequency is equal to 1 over time period. 1 over time period. Got it, dear? Right. Next subheading. Please write the velocity of waves. The velocity of waves within brackets V. The velocity of waves within brackets V. Right. Under that, please write the displacement of a wave for a unit time. The displacement of a wave for a unit time is defined as its velocity. Displacement per second is velocity. Unit time mean per second. The displacement of a wave per unit time. The displacement of a wave per unit time is defined as the velocity. Is defined as the velocity. Got it? Next star point. Let us consider a wave. Let us consider a wave with a time period of capital T. With a time period of capital T, comma, frequency of simple f, frequency of simple f, and wavelength of lambda. Let us consider a wave with a time period of capital T, comma, frequency of simple f, and wavelength of lambda. And wavelength of lambda. Got it? Next star point. Let us consider when the wave travels. Let us consider the situation. Let us consider the situation when the wave travels a distance equal to its wavelength. Let us consider the situation when the wave travels a distance equal to its wavelength. When the wave travels a distance equal to its wavelength. Right. Look at board here. So the wave travels a distance equal to its wavelength. It means, it means wave has completed one cycle. Draw this figure. The wave has traveled a distance of lambda meters. The velocity of the wave is v meter per second. Draw this figure here. Right? Let us consider the situation when the wave has traveled a distance equal to its wavelength. Right? Draw the figure. below the figure, star point and right. When the wave travels when the wave travels a distance equal to its wavelength. When a wave travels a distance equal to its wavelength. A distance equal to its wavelength, comma, it has completed one cycle. It has completed one cycle. Star point, when a wave travels a distance equal to its wavelength, comma, the wave has completed one cycle. Same line, same point. The time taken to complete one cycle is the time period. The time taken to complete one cycle is the time period. Within brackets, capital T. The time taken to complete one cycle is the time period, within brackets, capital T. Same line, same point. Therefore, the time taken to travel, very important. Therefore, the time taken to travel a distance equal to wavelength. Therefore, the time taken to travel a distance equal to the wavelength. A distance equal to the wavelength, comma, is equal to the time period. Is equal to the time period, within brackets, capital T. Therefore, the time taken to travel a distance equal to the wavelength, comma, is equal to the time period, within brackets, capital T. Within brackets, capital T. Read that star point one more time, the final star point one more time. Read. Okay, dear. Next star point. Let us apply the following equation. Let us apply the following equation to the wave. Let us apply the following equation to the wave when it travels a distance. When it travels a distance. When it travels a distance equal to its wavelength. Let us apply the following equation to the wave, comma, when it travels a distance equal to its wavelength. Right? Look at both. It means when the wave travels a distance of lambda, we are applying this equation. What is the equation we apply? Velocity, again, velocity equals displacement divided by time taken. Write this equation here. Velocity equals displacement divided by time taken. We apply this equation when the wave travels a distance of lambda. Right? So displacement of the wave lambda, time taken to travel a distance of lambda is the time period, capital T. Then look at board. Lamai, look at board. Velocity, normally represented by the letter V, displacement of the wave lambda. When the wave travels a distance of lambda, we say it has completed one cycle. Time taken to complete one cycle is the time period, capital T. Therefore, time taken to travel a distance of lambda is capital T. Who would like if I explain this again? Right, again. When the wave travels a distance of lambda, we say it has completed one cycle. Time taken to complete one cycle is the time period capital T. Therefore, capital T is the time taken for the wave to travel a distance of lambda. I have given that description in the star points also. Is it clear now, dear? Right. Now, look at board, don't write. Let me write this equation as 1 over capital T into lambda. Lamai, what is 1 over capital T? What is 1 over capital T? 1 over capital T is the frequency we have proved. 1 over time period is the frequency. Therefore, we get V equals F lambda. So, as science students, you should know how to prove the equations. Normally, I prove all the equations that I teach you. Please write up to this. V equals F lambda. That's how to prove it. This is clear. So you should practice how to prove these equations. Please write example. Example. The velocity of sound in air, very, very important. The velocity of sound in air is 330 meter per second. 330 meter per second. Full stop. The frequency of a certain sound wave is 9,900 hertz. You know that we are able to hear waves in between the frequencies of 20 hertz and 20,000 hertz. The frequency of a certain sound wave is 9,900 hertz. 9,900 hertz. Full stop. Find the frequency of the wave. Sorry, find the wavelength of the wave. Find the wavelength of the wave. Can you do it, dear? Find the wavelength of the wave. Directly apply the equation V equal F lambda, find lambda. Do it. Find the wavelength of the wave. Apply the equation. Apply the equation. V equals F lambda. V is 330. F is 9,900. Examiner asks you to find the value of lambda. You get some decimal places, right? 0.9. 3. Let's see. 330 divided by 9,900 is lambda. Multiplication 9,000 something comes to this side as division 9,900. So lambda is subjected. Right? So far, so good. Then we can cancel out one of the zeros. Happy. So we get lambda equals 33 divided by 990 because 1 0 cancelled out. 33 divided by 3 is, 33 divided by 11 is 3. 99 divided by 11 is 9. Am I right, dear? 0 divided by 11 is 0. Can you understand? 11 times 3, 33. 11 times 90, 990. Good. Lambda equals 3 divided by 3 is 1. 90 divided by 3 is 30. 1 over 30 meters. Who got this answer? Great. Right. If you divide, what will happen? Some students, they want to divide and get the answer with decimal places. 1 over 30, 0. 10 over 30, 0. 100 over 30 is 3. 3 times 30 is 90. 10 remaining. Again, 100 divided by C. So 0.033 meter. Who got this answer? Right. Complete it. What are the other things that we want to learn? Next one is theory of superposition, creative interference, destructive interference. After that, stationary waves. What's the next in there? Stationary waves. From stationary waves, you will get past equations, essay equations, structural equations. So those things are very important. What are the important things here? Theory of superposition, creative interference, destructive interference. After that, stationary waves. After that, tuning fork and so on.